In this lecture, we're going to study about chemical energetics or energy from chemicals. Now, before moving on, we first need to define a few terms related to this topic. Uh, One of those terms is called enthalpy. Now, enthalpy is the symbol for enthalpy is delta H, and the meaning of the term enthalpy is that it is the net energy released or absorbed in a chemical reaction. So most chemical reactions, energy is either given out or it's taken in. So the net amount of energy that is released or absorbed in a chemical reaction, that is called the enthalpy of that reaction. And the unit for enthalpy, it would be written as J, or would also be written as kJ, which would mean kilojoules. J would stand for joules and kJ would stand for kilojoules. So joules is the unit for energy. Secondly, there would be other terms that need to be defined as well, and one such term is endothermic. Now, endothermic means that endothermic term would be used when energy is being taken in. It is either taken in, you can also say that it is being used up, or absorbed could be another word that can describe this. So whenever energy is being taken in, used up, or absorbed, you're going to use the term endothermic. So an endothermic reaction would be one in which energy is taken in. Uh, the sign for such energy is plus. So if it is written that you have plus 100 kilojoules, is written that an enthalpy of a reaction is plus 100 kilojoules, that means that 100 kilojoules of energy is being used up, taken in. There are many examples of such reactions. One is, we can take one example, that is the decomposition reaction, in which, for example, we can talk about the decomposition of calcium carbonate. It's an endothermic reaction. Calcium carbonate takes in energy and it breaks up into calcium oxide and carbon dioxide. So that is an example of an endothermic reaction. It is going to absorb energy, and only then will this reaction take place. So any reaction in which you have to heat the products or the reactants and then reaction starts, that's generally an example of an endothermic reaction. A second example could be, we can think of uh, evaporation. When we talk about evaporation, H2O liquid is converted into H2O gas, and whenever evaporation takes place, it absorbs energy. The molecules are going to absorb energy. You have to give it energy, and then that reaction would take place. So evaporation is another process in which energy is absorbed. A few more examples of endothermic reactions are, number three could be photosynthesis. Now, photosynthesis, if you've studied biology, photosynthesis is when plants make sugar from water and carbon dioxide using chlorophyll, and they absorb sunlight. And the process is that CO2 It reacts with water, which the plants absorb from the roots, and this gets converted into C6H12O6, which is glucose or a carbohydrate. We can balance this. There would be 6 CO2, and there would be 6H2O. Oxygen gas is produced as a result, and we can count the number of oxygen molecules. There are a total of 18. There's 6 over here, so there would be 6 O2 molecules being produced. So photosynthesis is another example of an endothermic reaction in which energy is absorbed, it's taken in the form of sunlight. And there are many forms of energy. There is electrical energy as well. So a fourth example is electrolysis. When we talk about electrolysis, it's basically when uh, when you do an electrolysis of NaCl aqueous, what happens is that it breaks down, current is used, electrical energy is used, sodium metal, uh, not sodium metal, we let's talk about the electrolysis of NaCl molten instead. What happens is sodium metal is formed at cathode and chlorine gas is given off at anode. So electrical energy is absorbed, it's taken in to convert NaCl to decompose NaCl. So that's another form of an endothermic reaction. We can now move on and discuss exothermic reactions. So exothermic would the term would be used when energy is it's released, or we can say it's given out, or produced. In If whenever energy is released, given out, or produced, term exothermic reaction would apply. It's an exothermic reaction. The sign for an exothermic reaction would be it will always have a negative sign. The unit for energy would still be joules or kilojoules, but the sign would be negative. So if you have if there's a reaction, it's written that minus 100 kilojoules of energy. That means the enthalpy of a reaction is minus 100 kilojoules, means that 100 kilojoules of energy is released, it's given out, not taken in. So that's an exothermic reaction. And examples of exothermic reactions are, some are very easily you can figure out on your own. For example, burning, that produces a lot of heat, a lot of energy is given out. Uh, it's also called a combustion reaction, and we can take the example of methane, which is CH4. It reacts with oxygen and it produces CO2 and water molecules. So that's an example of combustion reaction in which energy is released. So the sign of enthalpy is going to be negative. A second example is neutralization reaction. A neutralization reaction is one in which an acid, it reacts with a base and produces salt and H2O. So almost all neutralization reactions are exothermic reactions, and they release energy when this reaction takes place. We can think of a third example. We can think about condensation, in which H2O gas or steam gets converted into H2O liquid. That generally happens when, in the formation of clouds, the gas converts into liquid, and then that liquid precipitates, and you get rain. So that's an exothermic reaction. More energetic particles get converted into less energetic particles. So that amount of energy is then released. Now we're going to discuss why some reactions are exothermic, whereas other reactions are endothermic. If you think of any reaction, now a chemical reaction involves both bond breaking, so it's going to involve breaking of bonds, and it also involves the making of bonds. So a chemical reaction, uh, for it to occur, it involves the breaking of old bonds, and then only can new bonds be formed. I can take the example of, let's say, this reaction. We have H2, and it is reacting with chlorine. Hydrogen is reacting with chlorine, and it is producing HCl. And there are two molecules of HCl that are produced. I can show the bonds. In hydrogen, there is H2. In H2 molecule, there are two hydrogen atoms and they are bonded together. And in Cl2, there are two chlorine atoms which are bonded together by a single bond. And then you have two HCl molecules. So you have one HCl molecule in which H and Cl are bonded together. And there's another HCl molecule formed where one H is bonded to another chlorine atom. Now, if you look at this reaction, for this reaction to occur, the first thing that needs to happen is you need to break the hydrogen-hydrogen bond, and you also need to break the chlorine and chlorine bond. So the bonds broken are, or the old bonds that are broken are, there's one hydrogen bond that needs to be broken, and there's one chlorine chlorine bond that needs to be broken. Similarly, new bonds are formed, and in this case, the bonds that are formed, there's one H and Cl bond formed, there's another H and Cl bond formed. So there are two H and Cl bonds that are formed. So in any reaction, old bonds have to be broken and new bonds are then formed. Another thing that you need to remember is that bond breaking now bond breaking that is endothermic. It requires energy. It's endothermic. It's always going to have a positive energy sign, enthalpy sign, which means that energy is consumed when you're breaking bonds. So bond breaking requires energy, and the simple logic for that is, for example, if you want to break the hydrogen bond, you would need to split the two atoms together. You would need to pull this hydrogen atom to one side and this hydrogen atom to the other side. So that would require energy. You would have to apply a force, you would have to give it energy, and only then can the two hydrogen atoms split up into two separate hydrogen atoms instead of two hydrogen atoms which are joined together. You can take the example of a magnet. The reason why these two hydrogen atoms were sticking together was that they were negatively charged electrons in the center which were being shared, and these electrons were attracting the two nucleuses together. So there was an electrostatic force of attraction. You can take the example, a real world example of, let's say, the two magnets. Instead of an electrostatic force of attraction, you can think of two magnets which are sticking together. The north pole is attracting the south pole of the other magnet. So if you want to break them apart, you would need to apply force, you would need to give it energy, and only then can these two magnets separate. So in a similar way, the two hydrogen atoms are sticking together due to an electrostatic force of attraction, and to pull the two hydrogen atoms apart, you would need to give it energy. Similarly, bond formation is exothermic. The sign of the enthalpy is going to be negative, if there's bond formation happening, energy would be released. So bond formation releases energy, and just like the example above, you can think of two hydrogen atoms and they're apart right now, but these two electrons in the center are going to attract the two nucleuses together, so they're going to get attracted to each other. Eventually they're going to bond with each other. So the force of attraction is doing all the work. The force of attraction is already present. So all the work done is done by the hydrogen atoms themselves, and which is why they are the ones that are going to do the work. They're the ones that are going to produce energy. You can think of two. Similarly, you can think of this. We can take a real world example which you're more familiar with. Think of two magnets which are apart. This is the north pole of one magnet. This is the south pole of the other magnet. Now there's the force. There's a magnetic force of attraction between the two magnets, which is similar to the electrostatic force of attraction between the electrons in the center and the two nucleuses. Now, if you keep these two magnets close enough, you are not supposed to apply any energy. These two magnets are going to get attracted to each other on their own. They're going to do work, and that work would be done by them, not by you. So when they're doing work, they're going to end up producing energy. So the no, so the two magnets are then going to end up sticking together. So bond formation produces energy. The work done is by the atoms themselves. You don't have to apply any energy when bond formation is happening. So bond formation is exothermic. Now, using these two concepts, we can now try and figure out why some reactions are exothermic, whereas others are considered endothermic. We can take the example of combustion. Now, combustion is an exothermic reaction. The sign of enthalpy is negative. It's an exothermic reaction, and now we're going to justify why this reaction is exothermic. We can take the example of any reaction. Let's say we have CH4, and it's reacting with two oxygen molecules, and it's producing CO2, carbon dioxide, and there are two water molecules produced in this reaction. Now, this reaction is exothermic. This is a simple reaction where your natural gas, the cooking gas, is burnt with oxygen and it produces carbon dioxide and water. We'll try and figure out how many bonds are broken first. So, CH4 has 4 bonds. The carbon is bonded with 4 hydrogen atoms, and then you have 2 oxygen molecules, and the 2 oxygen atoms are bonded together by a double bond, so there are 2 molecules of oxygen, which ends up producing carbon dioxide. So this is carbon dioxide where 1 carbon is bonded to 2 oxygen atoms, and it produces 2 water molecules. A water molecule is one in which oxygen is bonded to 2 hydrogen atoms, and there are 2 water molecules formed. Now, in this reaction, for this reaction to occur, you first need to break the old bond. So there would be these bonds need to be broken. There's no carbon and hydrogen bond in the product side. That means that bond has been broken. Similarly, there's no oxygen bond in the product side. So that means the bonds between the water or the oxygen molecules has also been broken. So the bonds broken in total are, there are 4 carbon and hydrogen bonds that have been broken, and there are 2 oxygen bonds that are also broken. So that's the total number of bonds that have been broken. Similarly, new bonds are formed in this reaction. This bond was previously not there in the reactant. So this is a new bond that has been formed in this reaction. So there's 1 carbon and oxygen bond formed, and there's another carbon and oxygen bond formed. So the bonds formed are, the first thing is there are 2 carbon oxygen bonds that have been formed. Similarly, this bond wasn't there, so this oxygen hydrogen bond is formed. This oxygen hydrogen bond is also formed. This one is a new bond that is formed. This is another bond that is formed. So there are four oxygen hydrogen bonds that have been formed in this reaction. So that's the total number of bonds broken and the total number of bonds formed. And what we have studied is that bonds breaking bonds is an endothermic process, whereas making bonds or bond formation is an exothermic process. Now, since the overall reaction is exothermic, that means that more energy is released, so which means that more energy is released when bonds are formed and less energy is absorbed. Only then will overall the net enthalpy of the reaction is going to be exothermic if more energy is released during bond formation and less energy is absorbed during the breaking of bonds. And remember one additional point is that no two bonds are similar. There's a different force of attraction in each bond. So each bond, when it's formed, is going to have a different amount of energy is going to be released when that bond is formed. Similarly, for example, this carbon double bond oxygen bond that would have a different energy coming out when it is formed. This oxygen hydrogen bond that is going to give off a different amount of energy when it is formed. Similarly, this carbon hydrogen bond is going to it is going to require a different amount of energy compared to this oxygen bond. So all bonds are different. They require different energies for breaking them, and they require different. They release different energies when you are making them. So since our combustion reaction was exothermic, it was exothermic. That means that there was more energy being released in bond formation and less energy being taken in when you are breaking bonds. So this question that we try to understand, it comes very often in your Cambridge examination. So the answer to this question would be that if a reaction is exothermic, so if a reaction is exothermic, the reason why that reaction is exothermic is that more energy is released during bond formation, which also means that stronger bonds are formed. So more energy is released during bond formation, and less energy is absorbed or taken in during bond breaking, which would also mean that weaker bonds are being broken, which is why less energy is required. Hence, your net enthalpy of the reaction is negative. Net enthalpy, delta H, is negative or exothermic. In a similar way, in an endothermic reaction, the reason why a reaction is endothermic is that if you want to justify why a reaction is endothermic, so in an endothermic reaction, more energy is absorbed when forming bonds, sorry, when breaking bonds, which means that stronger bonds are broken. So more energy is absorbed when breaking bonds, stronger bonds are being broken, and less energy is given out, which means that weaker bonds are formed. So a reaction would be endothermic if more energy is being taken in and less energy is being given out, which means that the bonds being broken are very strong. They are requiring more energy, and the bonds that are being formed are weak, which means they're producing lesser energy. So the enthalpy of such a reaction would be positive. There would be a net energy would be taken in such type of reaction. One example of this reaction would be nitrogen is reacting with oxygen and it is producing two molecules of nitrogen monoxide. Now, the bonds that are being broken in this reaction are you're breaking one N triple bond N that is being broken. Similarly, one oxygen bond is also being broken. So these are the bonds that are broken in this reaction, and the bonds that are being formed are the two nitrogen oxygen bonds that are being formed in this reaction. So these are the bonds that are formed in this reaction. If the reaction is endothermic, that basically means that you have more energy being taken in. So bond breaking requires more energy, and since it's an N triple bond N and oxygen double bond oxygen, if you this bond is particularly strong, and nitrogen is present in air, and if you've if you have any general idea of nitrogen is very unreactive, it does not react with anything. Oxygen is in air, that is the one that is reacting with everything. It's the one that's participating in combustion. Oxygen is the molecule that is rusting iron that is present in your everyday household. So oxygen is the troublesome gas in air because it's very reactive. It's easier to break this bond, but nitrogen is very unreactive. It's very hard to break the bond. So bond breaking is endothermic, whereas bond formation is exothermic. But since the overall reaction is endothermic, that means more energy is being consumed when you're breaking bonds and less energy is being given out when you're forming bonds. So this is the reason why reactions are endothermic.